Welcome to Lecture 6. In this lecture, we're going to get going on finding electric potential due to continuous charge distributions.
In our last example last time, we took a set of 7 charges and we found the net potential at point P, which was right across from the middle charge. And we found this by doing the sum of the potential due to each charge, kq over r for each of the 7 charges. So that deals with discrete charges or point charges. What if we wanted to have a continuous charge distribution or a line of charge? So that's what we have here in the far right picture, continuous charge distribution. Well, we're going to use the same approach that we did when we tried to find the electric field due to continuous charge distributions. Let's take our 7 charges and squeeze them close together. As we squeeze them close together, we see that this starts to look like a line of charge. So then what we do is we take many small charges and squeeze them very close together. That's what makes a continuous charge distribution. So we have many small charges and they're all very close together. So then what happens is each individual charge we now call a small piece of charge, dq, it's a little bit of charge. Each individual contribution to the potential is now a small contribution to the potential. And the sum of each individual contribution to the potential becomes the integral of each small piece of potential. Okay, so there's our strategy. We'll remember here that dV, the little bit of potential, is going to be k times the little bit of charge divided by the distance. So this is what we did with electric fields. We're going to do this approach again with potential. I'm going to stress again here now that with our electric fields, that was a vector quantity and we had to think about the vector components. And sometimes we had components canceling. For example, the electric field, due to this system of charges, would only have an x component. Electric potential is a scalar, so we're not going to see any cancellation of components because there are no components. Okay, let's get going on finding the electric potential due to a long line of charge at point P, which is some distance from the midpoint of the charge. We really took our time when we did this as an electric field example. A lot of the same ideas carry over, so I'm not going to do this one quite as slowly. Let's put on a coordinate system. I'm going to take my plus y-axis going up through the center of the rod. I'm going to take my plus x-axis horizontally perpendicular to the rod and going through point P. So there's my coordinate system. My origin is at the center of the rod. I need to identify a small little bit of charge, which I will call dq. So there's my little piece of charge dq. I need to put on my coordinates. Y is from my origin to my little bit of charge dq. Now my q looks remarkably like a y. I'm just going to erase that and put dq in there. There we go, that looks better. Y is my coordinate from the origin to where dq is. Y is variable. X is from my origin to where point P is. X is constant. My little bit of charge has a little bit of length in the y direction. So the length of my charge is from here to here. It's a little bit in the vertical direction, so I'm going to call the length dy. The overall length of my rod, we're given that it's 6 millimeters long. For right now, I'm just going to call that L. Let's do the problem all in symbols, and then we'll worry about the numbers later on. Okay, so there's my picture. That's all set up. Let's get started by writing down that a little bit of potential at point P due to my little bit of charge dq is called dV, and dV is k times dq divided by r. Now that I've written down r, I'm going to put r in my diagram. It's the distance between my charge and my point from here to here. So r is equal to the square root of x squared plus y squared. R is also going to be a variable because it depends on y. To find my net electric potential, I have to sum up all the bits of potential. I have to do the integral. So I've got the integral of k times dq divided by r. Notice I'm not finding any components here. That's because electric potential is a scalar. It does not have components. I know what I'm going to fill in for my R. What I'm going to fill in for my dq is the same as what I did for my electric field problems. My little bit of charge is equal to the charge density lambda times the little bit of length dy. So lambda equals linear charge density. That's going to be the total charge divided by the total length. So the total charge is 8.75 times 10 to the minus 9 coulombs divided by the total length, which is 6 millimeters. I'm not going to find that number right at this moment, but that's a value we're going to use now in a little bit. Okay, let's keep going with our potential. So potential, the net potential is the integral of k times dq, which is lambda times dy, divided by r, which is the square root of x squared plus y squared. Let's take our constants out in front of the integral. So k is constant, lambda is constant. We've got the integral of dy divided by the square root of x squared plus y squared. Okay, what about the limits of our integral? Because we're going to need those. Just like with electric field, when we're finding the net potential, we have to integrate over the thing that has charge. The thing that has charge is our rod. So we have to add up the contribution due to the entire rod. So we'll start at one end, down here, and we'll stop at the other end. So down at this end, this is where we'll begin. This is our y initial. Down here, y is equal to negative L over 2. So the origin is at the center. The total length is equal to L. So this bottom half of the rod has a length of L over 2. So the bottom coordinate of the bottom end is negative L over 2. Likewise at the top, where we'll stop with y, that's got a coordinate of plus L over 2. Okay, so the limits of our integral are from the beginning, the bottom of the rod, minus L over 2, to the top, plus L over 2. Okay, we're good to go for our integral now. You can do this by hand if you wish, or you can look up the result in a book. I shall choose to look it up in a book. And the answer is natural log of y plus the square root of y squared. Oops, I meant to say x squared. I want it to match what I had before. Of x squared plus y squared. And then that has to be evaluated at the limits of L over 2 and minus L over 2. Okay, so let's get going on those limits. So my net potential is going to be k times lambda, put in a big set of brackets. First we'll put in y equals plus L over 2. So that's going to be the natural log of plus L over 2 plus the square root of x squared plus y squared. L over 2 all squared is going to give me L squared over 4. Then I have to subtract the value where y is equal to negative L over 2. It's almost the same as the first value, but not exactly the same. Negative L over 2 all squared is still plus L squared over 4. Okay, so there is the expression. We're pretty close to done here, but we can simplify it a little more. To keep going, to simplify our expression, let's use an identity that says the log of A subtract the log of B is equal to the log of A divided by B. So let's use that in our expression for potential. Now our potential is V equals K times lambda times the natural log of L over 2 plus the square root of x squared plus L squared over 4 divided by minus L over 2 plus the square root of x squared plus L squared over 4. Okay, you could maybe simplify this a little further, but this is pretty much okay for now. So this is our expression for the electric potential at point P, which is a distance x away from the midpoint of the rod. We're given some numbers here, so we'd like to find the value of this electric potential. So for our values, we're given that the length of the rod is 6 millimeters, 6 times 10 to the minus 3 meters. We're given that the net charge on the rod is 8.75 nanocoulombs, 8.75 times 10 to the minus 9 coulombs. And our distance x is the distance away from the rod. That's a half of a millimeter, 0.500 times 10 to the minus 3 meters. Okay, I think that's all of the numbers we need for in here. We'll just put in a reminder that our lambda is equal to q divided by L. So rather than me substituting all these numbers, that's a little bit boring to watch. I'm just going to go ahead and write down the answer that I got when I put this in the calculator. And the answer I got when I put this in the calculator was 65,322 volts. So that's the size of the potential at that distance away from the midpoint of the rod. Now, when I wrote this example that we just did, I picked my numbers quite on purpose. The rod we just did had a length of 6 millimeters and a net charge of 8.75 nanocoulombs uniformly distributed. We just found that the total potential was 65,322 volts. This has some things in common with the last set of discrete charges we did at the end of the last lecture. So there I had 7 charges. The total charge was 1.25 times 7, or 8.75 nanocoulombs, and the net length of that distribution of charge was 6 millimeters. So this is an example where we had 7 discrete charges, and here's where we turn that into a continuous charge distribution. When we look at the potentials, those values are kind of close. They're both kind of on the order of 6 times 10 to the 4, but they're not exactly the same because the distribution is not exactly the same. But they're kind of close because they are a similar sort of thing. They're